Okay, so let's continue. Recall what we had last time. Last time we discussed supersymmetry algebra, and more exactly we solved at nth supersymmetry algebra. Kind of extended supersymmetry. Which has the form H, I and J go from 1 to n. We discussed some special cases, which are n equals 2 and n equals 4. And well, the main properties of the Hamiltonian. So this is the Hamiltonian, quantum mechanical Hamiltonian. So there are some general properties which follow from the form of the algebra. So one, that it's positive definite, non-negative. Second, that if it has a zero vector, then it's a zero vector of all q's. All q's annihilate the states for all from 1 to n. And for n greater or equal than 2, the corresponding spectrum is at least twice degenerate. I mean, the spectrum of positive energies. So if E greater than 0, so E means eigenvalue. Then the energy level at least twice degenerate. And the reason for this is the properties of the algebra, of course. So we have that E is the commutator Q is bigger, and we have the Q squared is 0. And so Q can be brought to some Jordan form with 2x2 blocks. 0, 1, 0, 0, 0, 1, 0, 0, etc. We have several blocks, but they're all 2x2 blocks because the anti-commutator has to be E. So that means that there is at least twofold degeneracy. And if you have n greater than 2, then actually you should realize that the corresponding algebra, the restriction of the supersymmetry algebra to the certain energy level of the Hamiltonian. So if you have n generic, general n, corresponding algebra, delta IJE is just a Clifford algebra. So this is a Clifford algebra. Dimension n. And from general properties of Clifford algebras, it is known that the corresponding representations are at least so the minimal non-trivial representation, so dimension representation is 2 to the integer part of n over 2. So this would be the degeneracy of the corresponding level, the degeneracy of the corresponding level. For example, I mean, this is easily, in the case of, most easily seen for the case of n even, but it's n. So the example, n equals to n. Maybe I should write 2 to m, n equals to m. Then you can form the complex supercharges utility k, which is by definition q2k is minus I uk minus 1, k from 1 to m. Then you form a vacuum state, which is filled by all q tilde. And the corresponding representation is then the span of all q tilde k1 dagger, etc., q tilde ki on the vacuum. And this has the correct dimension. So this is just like fermionic vector space. I mean, q tilde, they are and sorry. And q tilde k. Delta j. So it's just this. This is the dimension of this is 2 to the power m states in this case. Okay, so these are the properties of the properties of representations, and as we have seen, there is a double degeneracy for n greater or equal than 2. But in principle, for n equals 1, that might not be the case. So if for n equals 1, the algebra is more trivial. So n equals 1, we just have that 2q squared is h. So the spectrum might not be degenerate. So as an example of this, you can take just h h a positive. We have an example. Take h positive definite matrix. Matrix with distinct eigenvalues. Then q is just the square root. And the spectrum will be simple, so no degeneracy. And yeah, we'll see some another example. Yeah, maybe another example. So this is example 1. This is kind of a completely trivial example. So a slightly less trivial example, which is particle on a circle. So take a particle circle with twisted boundary conditions. So we'll take, so the Hilbert space here will be integrable function from a circle. But well, okay. So I mean, so I'll call this alpha, L2 alpha. Means this will not be really functions on the circle, but quasi-periodic functions on the circle. So alpha here means that our functions will be of the periodicity that psi of x plus 1 is e to the 2 pi I alpha psi of x. And clearly you can still define the L2 space of quadratically integrable function. with such alpha is a real number. And the Hamiltonian, the usual free particle Hamiltonian, which is minus 2 over dx squared. So the space of functions obeying this quasi-periodicity, functions from the space can be expanded in a Fourier series of the form psi is a and belongs to Z e to the alpha I n plus alpha x psi n. So, and the eigenvalues of the Hamiltonian, so the eigenvalues analogies. But by acting on these functions, we get that En is 2 pi squared and n plus alpha squared. And in general, this spectrum is simple. So, a simple spectrum. Generic alpha. Yes, and of course, here I mean that we still can extract the square root of the Hamiltonian, right? We can just say that Q is so from here, Q is I d or dx, maybe 1 over the square root of 2. But there's no doubling of the spectrum, so doubling of the spectrum can still occur for some values of alpha. For example, alpha is 0, right? No, doubling of the spectrum. Yeah, there can be accidental degeneracies. For example, if alpha is 0, then n and minus n. But that's because for alpha equals 0, there is a parity symmetry. So it's unrelated to supersymmetry. So I'm just saying that this is an example of kind of n equals 1 algebra, representation of n equals 1 supersymmetry algebra in principle, formally speaking, but without the degeneracy. So this is well, in our language, this would be kind of a degenerate example, something we don't want to have. And so the reason why this happens here, and it should not happen in other examples, is that, in fact, you should consider a representation. So last time we talked about superalgebra. So it's natural to consider representations of superalgebras on supervector spaces. So everywhere in what follows will require the representation space, which I call H here. This is our Hilbert space, okay? So the representation space should be or must be integrated with a clear, and there's some compatibility relation that the odds, so the superalgebra is also Z2-graded. So the odds generators of the superalgebra, when acting on a vector of given parity, changes the parity. The even generator of the superalgebra doesn't change the parity, right? So, so actually, as far as I know, so in theory of superalgebras, this is always the setup that people consider. So always consider representations on Z2-graded spaces. So you can compose H 0 plus H1. So for example, so we had our superalgebra as G0 plus G1. So G0 kind of maps H0, H0, H1 to H1, and the elements from G0, I mean G1, H0 to H1, to each other. So in the language of supersymmetry, this is usually formulated as a statement that there is some operator -1 to the f called -1 to the f called fermion number, fermion parity. And what it does, its main property is that its square is 1. This is some operator in H. Let's see. And it anti-commutes with the supercharges. The Q's we call the supercharges. I didn't mention last time. It's this one. This is yeah, this is the same as requiring this Z2 grading on H. So -1 to the F on H equals H for H 1 to H0 -1 to the F. So the point is that if there is a if you have an n equals 1 representation of an n equals 1 algebra on a Z2 graded vector space, then you automatically have a representation of an n equals 2 algebra. So plus 1 with this -1 to the F operator, it will automatically upgraded to n equals 2. Yes. And the reason is that we can now construct, so we have here, so in n equals 1, we have this real supercharge, which we call Q real, which that Q real squared is real with real H. Now we can construct a complex supercharge. Q complex, let's call it, or just Q, so Q of Q, which by definition is Q to the Q real times 1 over square root of 2, 1 plus and then Q dagger is then by an explicit calculation, you check that Q squared is 1/2. This is QR. commute this here. This changes sign. So this is 0. And well, another simple exercise is to check that the anti-commutator of U dagger is still H. So this means, well, these two properties that is squared is 0. This mean that it's an n equals 2 algebra. This is n equals 2. So we get kind of an additional supercharge out of this parity operator. So since we will always require that we have a representation on the Z2 graded vector space, actually we can forget about n equals 1. The upshot of this discussion is that we can forget about n equals 1 and just discuss n equals 2 as our simplest example. So for this reason, actually, at least even mostly in the old literature, people call this n equals 1, they call it n equals 1/2. To denote that it's not really a genuine supersymmetry algebra. But so in some cases,
so the question that when from n equals 1 we go to n equals 2, the spectrum becomes
yes. So the spectrum will always be degenerate.
Yeah, no, I mean, even if we take n equals 1 with no degenerate spectrum, by adding -1f, we get...
Yes. Yeah. I mean, of course, you can also think of it just as basically by adding -1 to the f, you kind of get the Clifford algebra again, right? Because it's two-dimensional Clifford algebra. So that's another way to say. Or you can just say that you have this Z2 graded vector space. So yeah, from now on, we'll forget about n equals 1. And well, sometimes we'll remember about it in the context of superspace, but we should have in mind that actually it has n equals 2. So I've used this operator. So this operator is just like a formal notation, -1 to that. But sometimes you actually have an operator called f. In many systems, in many supersymmetric systems, you have a operator called f. So often has the fermion number. In this case, it's really called fermion number. F. And this means that our H is not only Z graded. And the Z2 grading is kind of a subset of the Z grading, right? I mean, you can always take odd and even gradings and declare them to be H0 and H1. So that means that this is composed as HQ belongs to Z. And then, I mean, you can always recall this, reinstate the Z2 grading. So Z2 grading is just even and odd subspaces. So what we call maybe not so great. I'll call it like this HQ, and then H0 is some Q belongs to Z. The H1 is Q belongs to Z plus 1. So this fermion number operator we require that our supercharges, they raise and lower the fermion number, which means that F and Q Q and F on Q bar is minus. And F commute. So therefore F commutes with H. So F is a bosonic operator. So F belongs to, we can formally extend our superalgebra to say that F belongs to, by saying that F belongs to G0. So in our notation of the previous lecture, F is the same as the generator E1 of U1/1. So SU11 has the automorphism F1 goes to the I alpha F1, F2 goes to the e to the minus I alpha F2. So U11 is the extension by this automorphism, I mean the infinitesimal. So F, this fermion number operator generates this automorphism. And most of the time we'll be studying systems with U11 symmetry. We'll be studying representations of U1/1. The reason why I mentioned it was. And in this case, you can, so in this case, -1 to the F makes that direct sense. Operator -1 to the F is literally the, so this is -1 to the F. The exponent -1. So the next question is to construct some example of supersymmetric quantum mechanical system. To this end, we might start just with mechanical system. So some symplectic manifold, so on and so forth. So we want to realize this algebra that we have. Basically, is the algebra of vector fields on some supersymplectic manifold. So mechanical system. Supersymmetric. So how can we do that? Well, in general, we can, when we have some action of a Lie group or Lie algebra acting on our symplectic manifold, some symplectic manifold, symplectic form. So the Lie algebra has some generators TA. Some commutation relations. And we want to say T1 equals H to be our Hamiltonian for system. So we can simply take, so to each to each TA there is some vector field. And we assume that it preserves the symplectic form. In this case, we can form a Hamiltonian function for this corresponding to the vector field, which is called the moment map. Same as Hamiltonian. There is a maybe to TA next to UA. So this is a function on M. This moment map. Function on M. Such that the Poisson brackets of these mu's will produce the algebra of the that we started with. So we mapped this abstract Lie algebra of vector fields to this Lie algebra of Poisson brackets. So let's implement this idea here, and then we can just take one of these mu's as our Hamiltonian. So in our case, the mu that we want to take corresponds to this central element H. So nicely enough, in our case, if we pick T1 as our H, it will also commute with everything. So actually, this mu will be in involution. So our mu equals H. In our case, this mu will be in involution with all the other mu's because it's central element. So in the present case, let's take for present case an implication to the supersymmetry algebra. Let's take M as being M omega as being C1/1. So the simplest thing we can do is we can just take a linear vector space and a linear action of our linear representation of our symmetry algebra. That's what we're going to do. So we take C1/1 and I times so this is an even element A, and psi is a Gaussian variable. So C1/1 means there is one coordinate, one even coordinate, one odd coordinate, one Gaussian even, one Gaussian odd coordinate. And this symplectic form is by construction preserved by the action of U1/1. So omega preserved invariant with respect to the group or the algebra. Let's say the group U1/1 that acts as A psi. So the vector A psi goes to G times A psi. So sorry, G maybe is not great notation. So G tilde. So G tilde log U1/1. We have picked a symplectic form in such a way that it's by construction invariant with respect to U1/1. So here we just have G tilde dagger and G tilde, which by definition is 1. And let's construct the corresponding moment map. So what is H here? Which transformation corresponds to the action of H? Well, remember that H was basically an identity represented by an identity matrix, right? So now notation from last time, H is 0, which is just identity matrix. So in this case, this means that a psi goes to I to the alpha a psi. This is just the U1 inside U1 inside U1 1/1. And what's the corresponding moment map? Well, in fact, since we have invariance with respect to U1/1, we can construct the whole all the generators at once. So we can construct the bilinears Lij. Maybe let me call this chi. This vector will be called chi. So Lij is chi I dagger, chi j. So these are the generators of U1/1. And these are precisely the moment maps for the action of U1/1. These are the moment maps. So I've written all the moment maps for the action of U1/1. So in particular, our supercharges are the off-diagonal parts of this, and H and F are the diagonal. So here Ij is 1, 2. So let's write out H explicitly. So so H is a trace of L. Which is chi1 dagger. Chi1 plus chi2 dagger chi2, which is a dagger A, psi dagger psi. So this is our Hamiltonian. And in fact, this is nothing but the so-called supersymmetric harmonic oscillator. Oh. This is well, why? Because if you forget this fermionic part, this is just the Hamiltonian of the harmonic oscillator up to some shifts. But here, you see, as opposed to bosonic theories, there are no shifts here because the energy, the ground state energy, can be 0 or higher. So I mean, the ground state energy is somehow fixed by the algebra. So yeah, I mean, if it's 0, you cannot shift it really away from 0. So so what are the supercharges here? So the supercharges are just the off-diagonal elements of this Lij. So Q dagger, Q is L12, L21, psi dagger A, U dagger is the L12, is psi A dagger. And the fermion number is, well, here we will define it as L22, which is psi dagger psi. So yeah, there is some freedom in defining this because you can add the central elements to it. So here, this is not really E1, it is like E1 plus E0 or something like that. This notation. Okay, so, and in principle, this psi and A, they have a Poisson bracket that you can derive from the symplectic form. I will write it down explicitly because we will straight away pass to the quantization of the system. So we will write out commutators. So we will now actually, instead of vector fields on the manifold, we will now have some representations in some Hilberts. So quantization here is elementary. You just say that A with A dagger is 1, and psi with psi dagger inside commutator is 1. And then just treat these guys as operators acting on the corresponding Fock space. So by Fock space, so our Hilbert space is Fock space. Which is just the span of, can be written as f of A oscillators times f of psi oscillators. And Fa, by definition, the span of A dagger to some power acting on the vacuum, where the vacuum is annihilated by A, and the psi. And there are only two states, vacuum and psi dagger is the vacuum, where this vacuum is annihilated by psi. Fock space. And so let's compute the spectrum. So the eigenvalues of our Hamiltonian. So the Hamiltonian here.
So here, what is the same?
Yeah, it isn't the same. Yeah, it's A bosonic, A bosonic. I mean, in the tensor product, we just take A like a bosonic.
Yeah, so
Yeah. I mean, here we take a tensor product. So we take this. So the spectrum is given by just E and M, which is N plus M, where N is these are the occupation numbers of these A's and psi's. So N is 0, 1, 2, and M is just 0 and 1. So that means that we only have En0, which is N, and En1 is N plus 1. So if we draw these towers of states, so we have one tower, 0, 1, 2, etc., and then this other tower. This is En0, En1, like this. Right, so for the ground state with energy, we have a ground state with energy 0, which responds to N and M equals 0. And then the first excited state has energy 1, and you can either have 1, 0 or 0, 1. So this is 0, 0, or 1, 0, or 0, 1. And here you can have 2, 0, or 1, 1. Right, I hope the pattern is clear, right? So there are two states at each level, except at the energy level, which is compatible with what we discussed before. So this is a ground state. These are excited states. They come in pairs. We have the general. Maybe let's take a break to continue with more general models. This is all about the harmonic oscillator, so we'll see how to generalize it to more interesting models with potentials. So let's see here. So, yeah, let's pass to considering more general models. So far we're done with harmonic oscillator. We'll still return to the harmonic oscillator when we discuss about superspace and so on, but for now we're done with it. And the models with potentials. So in this corresponds in the language of the previous half lecture, this corresponds to symplectomorphisms. So symplectomorphisms realized by nonlinear vector fields. So the Hamiltonian is defined with some vector fields, which preserve the symplectic form, but in general it's nonlinear. Nonlinear means its components are not linear in the variables. So, well, in usual quantum mechanics, we're used to problems with potentials. So we have the Schrödinger operator with a potential. So harmonic potential is only one of them. So we're interested how to reproduce supersymmetric models with arbitrary potentials. That's the point of this discussion. So to see how to generalize from the harmonic oscillator, let us notice that actually to specify the n equals 2 supersymmetry algebra is basically the same as specifying a complex supercharge such that its square is 0, right? Because then we just define the Hamiltonian as an anti-commutator of Q and Q dagger, and this automatically commutes with Q. So supersymmetry algebra is automatically realized. So basically, it's enough just to specify Q. In the case of the harmonic oscillator, Q for harmonic oscillator, what we just discussed, Q was just psi dagger A. And this was, of course, important because psi dagger is important. But we can just simply replace this, generalize, by saying that Q is psi dagger A, capital A, where now A is an arbitrary bosonic operator, right? This could be arbitrary. So in particular, we do not require that it satisfies the commutation relations of the oscillator. And in this case, the Hamiltonian is the anti-commutator of psi dagger A, psi A dagger. And this is A dagger A plus psi dagger psi, commutator of A with A dagger. So sometimes it's useful and it's customary to parameterize psi in terms of a psi is our two-level system, right? So psi we can parameterize maybe it's not the right word, but just write psi is a 0, 1, 0, 0. Psi dagger is 0, 0, 1, 0. So that means that the Hamiltonian in this language, it becomes the matrix Hamiltonian. Form A dagger A, 0, 0, A dagger. And so now I would like to, like I say, we would like to study problems with Schrodinger-like operators with potentials. So we will restrict to some particular class of A's. So to get some, so we want to consider Hamiltonians that in the bosonic sector become Schrodinger operator. So we want that H restricted to bosonic sector. Bosonic sector means that you put F equals psi dagger psi equals 0. That it becomes a Schrodinger operator with potential. E of X. And so we use the ansatz. So this is what we want. We use the ansatz that A is d over dx plus w prime of x dagger minus and our bosonic vector space here is A for H0 is L2 R as we usually have, and H1 is C2. So I'll just say that this C2. Yeah, so actually both H0 and H1 are copies of L2 of R. Yeah. So okay. And this function W is called a superpotential. Later it will be clear why we write W prime. So like derivative of the superpotential. So H0 is a dagger A. So this is H0 is by definition our bosonic Hamiltonian. Is then you open the brackets and you see that this is So this thing, what stands here, is therefore our potential. So this is by definition the potential. So this is the relation between the superpotential and the potential. So from W, U is defined V by this formula. But it might not be easy to do the reverse operation. So to solve this equation, get W out of V. So we should really view our superpotential as our primary object, we kind of specify in the supersymmetric system. So as an example, we can take the previous case of the harmonic oscillator. So W squared over 2. Well, it means that V squared minus 1. So this is a harmonic potential. You see, we automatically get some shift of the potential, which ensures that the ground state has zero energy. So we subtract this subtraction. Ground state energy is included by subtraction. So, of course, we also have a Hamiltonian acting in the fermionic space, so in space with fermion number 1, which we can call 1, which is the opposite product in the opposite order, which one is a dagger. And this is W prime squared plus second derivative. So they differ by sign. Sign minus here and plus there. So suppose that F0 is an eigenstate of H0. Suppose that H0 F0 is E F0. So that means that H of 0, 0 is E 0, 0, right? Because now H was the diagonal. H is H0, H1. So this vector has the property that Q dagger, it's annihilated by Q dagger. But our eigenspaces with non-zero energy are doubly degenerate. So that means we can act on this by with a supercharged Q, and this will give us psi dagger A 0, 0, and this gives us 0 A F0. This must also be an eigenvector of H. So also the same energy, H. But this stands in the lower position. So that means that actually H1, it's an eigenvector of H1. So this is AF0. So So the point is that the eigenspaces of H0 and H1, so this double degeneracy in the supersymmetric language can be rephrased in the purely Bosonic language as that there are two Hamiltonians, H0 and H1, but their eigenspaces are in one-to-one correspondence. And the eigenfunctions are obtained by acting by A or A dagger. And the only exception is when E is zero. In this case, so if E is zero, then just this wave function A of zero is zero. So it doesn't exist. So if E just A of zero is zero. And our original wave function f00 is annihilated both by Q and Q dagger. As we already discussed. So there is, of course, more old school explanation of this. Is just that your Hamiltonian is we have so just an equivalent explanation. That maybe simpler one is that if f0 is an eigenvector of this operator, let's act on it with A. Then we just get that A dagger A f0 equals E times A of 0. So this is H0. This is H1. So this is just a gradient of this symbol. Okay, so the next topic. So here we've seen that there is some state with energy 0. In the case of the harmonic oscillator, is just is a single state with energy 0. So, but in general, these states with energy 0 are particularly important here in this kind of science. So that's 0 energy states. Let's discuss them. So one might ask if states with energy 0 exist in a given system. So in the situation, so the first question is, are there such states? In the one-dimensional problem that we're discussing so far, this is an easy to answer because because we have an explicit equation for this. So our Hamiltonian is just block diagonal. So they exist if one of the Hamiltonians has a 0 energy state. So this is only if either A of 0 is 0 or A dagger of 0 is 0. Just call it F. So which means here this means that d over dx this means that minus d over dx so this is one reason why we've put a prime here, right? So to simplify the solution of this equation here e to the minus w where f is e to the w. So we're considering a situation on a real line, and we want our wave function to be normalizable. So that means that it should go to 0 at infinity. So only one of these can be normalizable therefore. So we require that f belongs to L2 of R. And some examples. So there can be either 0 or 1. So either 0 or 1 solutions with an energy 0. And both cases can be realized. So example, the polynomial superpotential. Let's consider W of x, which is 1 over p plus lower powers. P is a positive integer. So f is to the minus W, belongs to L2 of R, or E equals to M, so even P, right? Because it goes to 0 and plus and minus infinity. So this is the case. So in the harmonic oscillator, here W of x equals 2, and so we know the ground state wave function automatically equals minus x squared over 2, the wave function of the harmonic oscillator. So on the contrary, for odd p, there is no normalizable wave function because for odd p, the W goes to plus or minus infinity. Goes to infinity at one infinity and minus infinity at the other infinity. So in this case, there are no zero energy states. So if P normalizable states, and usually the ground state with if E0, so ground state energy is greater than 0, so no zero energy states, then with some terminology that says that supersymmetry is spontaneously broken. Or if E0 is 0, then it's not spontaneously broken. This is some terminology that comes from field theory. Here, really nothing is broken. It's just property of the system. So this is some field theory jargon. Still, it's used also in quantum mechanics. So the question is, there's a certain numerical characteristic that tells you if supersymmetry is broken or unbroken, meaning that you have zero energy states or you don't. So there's a numerical characteristic. So versus 0 equals 0 versus 0 greater than equal. We just call the Witten index. of Wheaton index. And the Wheaton index is, by definition, we denote it by IW, is the trace over our Hilbert space minus 1 to the F to the minus beta H. So minus 1 to the F is this parity operator that we considered before. Or it can be also written as super trace of e to the minus beta H. Or Hilbert space H. This is which is the E2 graded. So here H curly is the Hilbert space, H straight is the Hamiltonian. So beta is a parameter. Beta is positive. The positive parameter. So the usefulness of this object is that first of all, it does not depend on beta. So and this is proven as follows. So let's compute the derivative. This is a super trace of H with minus H. And now we recall that H is an anti-commutator of Q with Q dagger. So then by using the Leibniz rule, we can write this as a super trace of Q with Q dagger e to the minus beta H. Here we use that Q commutes with H. And then this is 0 because the super trace of a generalized commutator is 0. So just for trace of in our whatever supersymmetry algebra, super trace is 0. This is a super commutator. Well, this is the reason for introducing super trace in the first place. That's the main property of super trace. So when you have a usual commutator, this will just be related to the usual trace. So so another way to understand this is why it doesn't depend on beta is that so the only dependence on beta could come from states with positive energies, right? Because this is a trace over, it can be written as a trace over energy level C to the minus beta EM, and then super trace of identity operator over this H equals EM subspace. But we know that for such representations, there is a double degeneracy, at least double degeneracy. I mean, such states are at least double degenerate, and one of them sits in the even part, one in the odd part of the Hilbert space. So the super trace is 0. So the only states that contribute to the Wheaton index are the ones with zero energy. Only ground states contribute. So in other words, we can write that the Wheaton index is a trace over minus 1 to the F over H0 instead of H. So this is, in other words, this is just the super dimension H0. So this is the states with energy 0. And yeah, it also follows that this is an integer, right? So first of all, because it's an integer, it's actually homotonically invariant, right? So a priori it depends on the Hamiltonian, but from the definition. But actually it doesn't. I mean, at least if you make a homotopy of your from one Hamiltonian to the other, then it's so that's the main property of homotopy invariant. So for example, so consider a family of Hamiltonians parameterized by variable t, which is the anti-commutator of qt dagger. So we have a family of supercharges, and t belongs to whatever 0 to 1 or something. So the same argument applies. So you can compute the IW over t, and we get this is beta as the supertrace t over dt. To the h, and in each of these you use, for example, here you can use that this is the anti-commutator of qt with dq over dt minus beta h, and the supertrace of it vanishes. It's essentially the same computation. Of course, this first computation can be thought of as the same kind of homotopy where beta is t. Multiply the Hamiltonian by t. It's useful to single it out in separate calculation. So that means that to compute this Witten index, you can actually deform your Hamiltonian in various ways and search for a simplest one where you can compute the zero energies technically. So if the Witten index is non-zero, then supersymmetry is unbroken for symmetry. So that means that there are zero energy states. This Witten index is the difference of bosonic and fermionic, I mean, degree 0, degree 1, odd and even degree zero energy state. So if it's not zero, there must be at least one such state. So it's a sufficient condition for supersymmetry to be unbroken. So sufficient condition for having states with E equals 0. So if index is 0, then this means that the number of bosonic, number of odd and even, so even is equal to the number of odd. So when you perform a deformation, pairs of such states can group into non-zero energies doublets and disappear from the E equals 0. So in this, so here you could perform a homotopy and get rid of the zero energy state. right? So pairs of such states combine and to under deformation homotopy and combine to IE not equal to 0 doublets. The degeneracy can be uplifted by some perturbation. So our favorite example, the harmonic oscillator. The reason why we discussed it, so there are applications of this wind index, but later on this will be related to homology. When we discuss sigma models, supersymmetric sigma models, this will be the wind index will be the familiar index of some Durham or the Dirac operator or something like that, the Dirac operator. So will be related to homology. And the ground states will be representatives of cohomology group. So this is presented. So the fermion number will be related to the Z grading on the cohomology, for example. So that's the future. So in harmonic oscillator case, have this fermion number above psi, and we have a ground state. So our ground state was this Z bosonic times Z fermionic that is annihilated by A zero and fermion number 0. So that means that the Witten index is 1. Tonic or even ground state. So if you have a odd superpotential, then the Witten index is 0 because there are no supersymmetric ground states. Whereas if, say, the superpotential is an even polynomial, the degree is even, then the Witten index is 1. Again, there's one bosonic ground state. But if you take Wx as minus x to the 2m, for example, then well, the second wave function is normalizable. We consider two wave functions, one annihilated by A, the other by A bar. So if you just swap the sign, these are swapped. So that means that the Witten index will be -1. So this is just, of course, this is kind of not very potential. This is just related to the change of grading, swap of Z2 grading on H. On the Hilbert. So it just depends what we call odd and even. The swap of what we call odd and even. Okay, so this is these are some basic on the Witten index and the zero energy states, and we will see later on some. We'll look at some techniques to compute the Witten index. So because it's a homotopy invariant, you might imagine that it's easier to compute it than like computing the, say, finding the spectrum, the full spectrum of your system, or finding the eigenfunction, right? It's some more crude invariance. I mean, mostly next time we will slightly deviate and consider some more general systems. So far we discussed systems with SU1/1 or U1/1 symmetry. So principle, nothing can U1/1. Nothing can prevent us from generalizing this to some other symmetry algebra. So next time we will consider U1/n symmetry algebras. So in particular, the example of the harmonic oscillator, the way that I presented it, of course, easily generalized to any symmetry algebra, acting like that, acting linearly on some symplectic vector space. And we'll see what the Witten index gives in this setup. This is although I should mention that this is not a conventional supersymmetry algebra. Like I said, it's some symmetry algebra that kind of makes sense to consider that makes sense in one dimension mechanics, but it doesn't naturally come from some. In general, does not naturally come from some higher dimensional theory or something where symmetry algebras are much more rigid. But in one dimension, there's much more freedom. So, like I say, nothing can prevent us just generalizing like this. So this was actually considered quite recently by Smilga. So, and it's kind of is an interesting result for the Witten index and so on. So we'll, as a slight digression, we'll speak about it next time. And for now, I think let's finish. Some questions. Yes. Or you can write the questions in the WeChat group, or you can also write me a WeChat message, in personal WeChat message. Right. Well, I guess not. Then I'll finish the recording and we'll finish today's lecture. See you.